If you look at the slides that is posted in New Future, there are a total of 3 PowerPoint slides talking about air and emission sampling. But for today, I'm going to use only this PowerPoint slide, which is number 5.1. Okay, number 5.1 with slide adjustment. Now, if you have already downloaded the PowerPoint slide from UFuture, you're going to realize that the subject code is different than the one that we are looking at here. That is because this PowerPoint slide was initially created to teach postgraduate students. So yeah, it is that high level. But to me, environment sampling is not really high level subject. It is like a undergraduate subject actually. So the same PowerPoint slides was used here. And the initial creator for this PowerPoint slide is actually Mr. Rustin Laiman, in which he was supposed to teach this subject for other groups, but because it's not part of the EPJJ activity, so I'm taking over lah. Yeah. Okay, so you were going to realize that this PowerPoint slide have a bit of redundancy. That means similar points may appear in several slides. So if that happen, I'm going to skip lah, whatever the points that is repeated so that we don't waste time. So to begin with, ambient air. Just for your information, ambient, the meaning for ambient means the original state, okay, the original state of the air. So when we're talking about ambient air sampling, that means we are conducting the activity to collect air samples at its original state without any source of pollution. So you can say that this is mainly the activity of DOE and also Jabatan Meteorology lah. Okay, so I'm going to bring you lah. Why is that too? I'm going to bring you through this slide, then you understand why. Okay. So why do we even need to take air sample? Now that is because in Malaysia, particularly, we have laws that is governed to control the air quality and the well-being of human. And for your information, this slide did not say anything about atmospheric chemistry, what and whatnot, because I assume that all of you have already undergo some basic training regarding atmospheric chemistry, how much proportion of gases around the atmosphere, and of course you also have like experienced several episodes of severe air pollution in Malaysia, particularly before pandemic, when we have annual haze event every year we have until the pandemic hits. I'm sure you know lah, the haze event. So that is where all this were going to pop up. We're talking about air pollution index, and Malaysia does have one. But what is written here is actually from United States. Because we don't call it National Ambient Air Quality Guidelines, we just call it Air Pollution Index. Just that. Yeah, there's no guideline regarding this one. Now, this guideline comes from United States, so we're just going to take this as like a material for learning, and so you have to realize, whatever that is mentioned by NAAQG is applied in United States only, but not in Malaysia. Yeah. Okay, the evaluation state of air quality resulted from implementation of ambient air quality guideline and emission control standard. So why this is so? Because if you look at the air pollutants, or the so-called the parameters, okay, the parameters that we're going to analyze in majority of the air pollution index, the pollutants are counted. I mean, the pollutants that are analyzed are NOx, that means nitrogen oxides. That is not only limited to nitrogen monoxide, that also expands to nitrogen dioxide. So there are two types of NOx gas. The other one is SOx. SOx is sulfur oxides. And similarly to NOx, they also have two, sulfur dioxide and sulfur trioxide. Which one is more dangerous? I believe you can search for yourself lah later. Okay. The other one is carbon monoxide, as we know, toxic. Too much of it might poison people. PM10, particulate matter. So that means we're going to look at um, how much of the dust particles, and with this size. PM10 means 10 micrometer, 10 microns, time 10 micrometer in terms of particle size diameter. Okay. TSP is total suspended particle. So that was related, but this one considered all particles, regardless of whatever the size, all of it comes under total suspended particle. Ozone. Now, if you don't know ozone, how it smells very pungent, just like chlorine, and it kills. Yeah, and it also causes cancer, of course. And lead. So what ticks me off is when I look at this, and straight away I know this is not for Malaysia, is that in Malaysia we do not measure lead. So there is a story why United States look at lead that seriously is because now United States is a very unique country where sometimes the toxic things might comes into their consumer product. So this also includes the paint that they use. Quite a lot of the houses in United States were painted with lead paint because lead was used as a white pigment in their paints, but it was phased out lah. But a lot of old houses, they still carry this legacy lah, of toxic lead dust in their own homes. And the other part is that they also use lead piping. But that is another story. Lead piping might cause water pollution. So that is another one. Today we're going to talk about air pollution lah. Yeah. So these are the so-called guidelines. And you can see from the first column, the gases or the pollutants that is the concern of NAAQG, as well as the levels that they are allowed. Now, something that you have to remember also, now for air quality monitoring, the so-called permissible level is measured based on a certain time frame. So you can look at some of the gases, they are measured, I mean, their standard is based on an 8-hour average or maybe 1 hour average. Now, some of them even longer, like for example, lead. Lead is not considered like a major contaminants or major pollutants. So the likeliness of it being around, okay, in the air is very, very low. So which is why they need more time to capture this lead from the air. And the others like still the same, 24 hours or maybe 8 hours. So you can see the average time very much depending on the levels that you want to measure against, versus the concentration that is available in the air. Okay, so this one depends on each of the criteria lah. Uh, but I just want to remind you now, out of all these level and guidelines, um, in Malaysia we only measured a few lah. Now, if you look at air pollution index in Malaysia, we do measure PM 2.5, PM 10, uh, NOx, SOx, ozone. Majority of them we do measure here, carbon monoxide as well, but not lead. That is for sure. Now we only measure lead if there is a request, a special request to have a look at it. Yeah. So that is for Malaysian air quality index. Yeah, what we're looking at. Okay, now with that, I will not going to talk too much about NAAQG, but there is an aspect, fundamental aspect, I will call fundamental aspect on how we would use this guideline. So if you look just now, the guidelines right here, they all uses ppm. So ppm is quite a arbitrary unit to be used because it can be based on the mass, okay, the mass concept, the mass basis, or maybe volume basis. However, if you look at the so-called clearer picture on how we can best imagine the concentration of one pollutants in the air, we're usually going to convert it into mass over volume unit. Now you can see right here. Um, so it could be volume per volume unit, or maybe weight over weight or weight over weight basis, or maybe weight over volume basis. That is because the pollutants that we are looking at, sometimes they are gas. If it is gas, that will be volume basis. However, if it is a solid like particles, they don't float around and they are not gas, they're solid. And the basis, the SI unit that we're going to use is mass over volume unit. So there is a high possibility that some of the standards that we're going to use may need to be converted from ppm to SI unit or vice versa. So the the way, okay, the approach that we're going to use in order to interconvert between ppm and also SI unit is by using this formula. This formula comes from ideal gas law. I believe you must have learned this in either secondary school or in your diploma. You must have seen this before. PVNRT. This is the ideal gas law that connects pressure, volume versus the number of mole and also the other constants like ideal gas constants and also temperature. So this is how they connect it. I know I have been through this and I don't quite like this formula because I remember I learned this under chemistry and also physics, which we are going to see again because these are the things that you will going to see in order to convert like, from ppm to microgram per cubic meter unit. So before we continue, a few things that to refresh you lah. Pressure, P represent pressure in atmosphere or 760 millimeter mercury, whereas V, the unit used is liter, N is in gram mole, or this is, you can say mole lah if you want to. Yeah, N, the unit is mole. R is the gas constant, which has a value of 0.8206. So very important for you to remember. If you want to take this value, then these are the unit. So which means that your P, okay, if you want to use, has to be in atmospheric unit as well lah. Otherwise, if you want to use this unit 760 millimeter per millimeter mercury, then the value perhaps is a bit different. Yeah, so R constant have several versions depending on what unit that you're going to use in the formula. Yeah, and then finally T, no question, it's Kelvin. So I'm sure you know what is Kelvin at 273. That is a unit at the degree Celsius. Yeah, that is a equivalent. So in order to calculate, now you need to derive. Yeah, you need to derive a suitable question out of that ideal gas law formula. So when we expand it, the n value equals to m versus mw, whereas m is the mass of sample, mw is the molecular weight of gas. So mass over molecular equals to mole, which is this one. And if you rearrange this formula, rho is the density of mass. Yeah. And if you rearrange this ideal gas formula, making mass over volume, that is exactly the density here, and that equals to P multiplied with molecular weight divided by RT. Okay, that's not the end of the story, yeah? Because in another assumption, if you look at the ppm unit, that is the ratio, okay? 1 in a million, as you can see right here. So if you look at the gas pollutants right here, the volume is 1 over 1 million, okay? 1 million of a total volume of the gas mixture. So there are several questions that you can see later on in which I will not going to go through for the interest of time. So I'm just going to let you have a look and you test it lah. So this is an exercise that you can do later, and there are furthermore exercise with answer. But I can see, but yes, you can see lah, it's quite straightforward, very easy. So I don't think I need time to explain this one. Okay, fast forward. Yeah, fast forward. Based on the formula, the ideal gas law formula that we have seen just now, if we divide by volume, okay, total volume, the other side also divide by total volume. This side, the left hand side of the formula, essentially represent the uh, the concentration in ppm unit. So if you look back at here, then this will represent the formula that you need to use to calculate. Yeah. So a little bit of rearrangement further, then this is the formula lah, that people usually use to convert, yeah, from ppm to the microgram per cubic meter unit. Okay, now that is because if you look up here, m, that is a mass. Now of course initially the mass is in gram unit, so if you want to convert, you pandai-pandai lah, you convert into microgram. Yeah, that is simple mathematics. Whereas volume here, initially is liter. So if you convert directly liter into cubic meter, that is cubic decimeter. So of course, again, you were going to need to convert lah back into cubic meter later on. So this is the formula that you can use to convert from ppm to microgram per meter, per cubic meter. Now, at this point, I do not have any question for you to test, but if you're going to see any one of these questions, is most probably going to be in the quiz question. Yeah, perhaps you're going to complain, oh, how cruel it is. You're going to give me this tough question in quiz. Uh, but yeah, I so far lah, yeah, so far I haven't give this kind of question in the quiz question. Quiz, they are fairly simple. Don't worry about it. Now, the only thing that I probably want to see this calculation, the you yourself using this formula, is in your assignment. I believe you will going to use this in the air sampling section. But if your assignment does have this component, I strongly encourage you, because in Malaysia there's nowhere that you don't have air pollution. So in your assignment, most likely you will have this part. And in order to convert ppm into the SI unit, this formula will need to be used. You can say lah, I am expecting you using this formula in your assignment. Okay, right. So for the interest of time, I also will not going to calculate this formula. I'm not going to use this formula for any calculation. And I'm going to let you do it yourself and have a look. Like, these are the examples how you can convert from ppm to microgram per cubic meter. And these are more questions lah, yeah, coming from here. So I will not going to touch this. And yeah, I'm going straight to the next part, which is the sampling. Yeah. So in this part, we're going to go through the general requirement for sampling analysis before we go into the techniques, the so-called technical part on how to use an equipment or what kind of equipment will be used, versus the requirements that is subjected by the local guidelines. Now, if you look at all 5 points right here, it is very similar. Yeah, very similar to the points that I have mentioned exactly last week during sampling plan, the design. Yeah, in which the first one, the survey for preliminary information is needed. So that, now why is that? Why do you need to know the preliminary information? Because there will going to give you a reason or a purpose on conducting air sampling. You don't do air sampling for no reasons, kan? Okay, now perhaps you're going to ask me, then why AQI? Air Quality Index, Air Pollution Index, API, yeah, in Malaysia, is conducted 24/7, 365 days a year. Why? For one simple reason, because air is very important for human well-being and also for the environment. Now, for your information, air pollution since several years ago have been identified by WHO as the major cause of cancer. It's not just lung cancer, for all cancer. So so we're not going to like a better world today because of the air pollution. Yeah, that is why air quality monitoring is so important, so that if there's any pollution, countermeasures can be conducted. Because trust me, even air pollution can happen naturally. Yeah, So it's not due to human who caused this air pollution, it's natural air pollution. There are two examples that I want to share lah, which is not in this slide. Number one is the in Philippines, probably 20 years ago, where there's a volcano eruption that caused all those dangerous gas to float around in the air, and it contaminates even the ASEAN region, including Malaysia. Another very famous event happens in an African nation. I forgot what is the name of that nation, in which it was also caused by some seismic activity that caused a large amount of carbon dioxide gas to be released, and it kills literally everyone within that region. So that is the reason why air monitoring is so important, because you never know, air quality suddenly change, and that might kill and wipe out the entire population. So that is why we look at air quality that serious. Yeah. So once you know why you want to monitor, then of course lah, you will know what equipments that you want to use, how many samples you want to put, and where do you want to put your sampling point. So these are the things that exactly what I've mentioned earlier. So I do not want to repeat it. Um, well, of course, don't worry, because why? After 6 weeks, you're going to do it yourself. Yeah, you're going to do it yourself. Yeah, together with your friends in other groups. Okay. So the survey now, what is needed in this preliminary information survey, that counts a lot of things, yeah. Because during this ambient air pollution sampling, you will need to collect a lot of information, qualitative or quantitative. Qualitative means you're going to look at the you're going to survey what are the possible source of pollution. Quantitative, how much they may contribute, how many source that may contribute, and where is exactly the location. So that gives you some idea. Okay, where do you start? Because usually the source of air pollution starts from some industries that might be involved in causing this pollution. And of course, you also need to look at why this pollution matter. Because if this pollution is going to the population and might cause danger to them, then you might establish, yeah, you want to establish a trail from the source to the population, the housing area, like for example. You need to establish that line in order to see if indeed there is a there is a movement from the source to the community. Yeah. And then of course, in that movement, the trail, it might be deterred or altered due to surface. Okay, the shape of the surface, we call it topography. Because if you have a hill, like for example Banjara Titiwangsa, whatever happens in the Klang Valley may not be directly transferred into the East Coast, for example lah. And that is very true. Yeah, that is very true. Because whatever happens, the pollution in Semenanjung may not transfer that quickly, like at least to Kuantan, to Terengganu, or Kelantan. Yeah. And then the population distribution. Now, this is even more important because why? If we say there is no population nearby or there's no damage, then yeah, probably no, there's no concern at all in order to conduct this sampling, because we only conduct this one that probably have an interest or a stake. Yeah, and that is the general population. We don't want them to like suffer or die due to this air pollution. Okay, land use pattern. Now this one will going to dictate lah how much of pollutants that will going to be released, because usually if you change the land use, okay, now let's say land use, original state of the land, what is it? Anybody can give me an example. Original state of the land, if nothing changed lah, how it should look like? Anybody can answer? If you look at Malaysia lah, originally, if there's no human, what is that? Any idea? Still don't know. Okay lah. I'll just let you know lah straight away without wasting time. Okay. Now, when we look at the original state of any land, if without human, then there's definitely forest, kan? Land without being changed or converted, original state is forest. And when we think of forest, automatically the air should be clean because there's no contamination or human activity whatsoever. But due to the human activities that comes in, logging first of all, logging. So first thing that you mentioned, once it is logged out, exposure and also dust comes out. See, if any land is being developed, dust first thing will comes out, and then the rest will going to be changed. Yeah. So a lot of things may happen when land use is changed, and of course climatology. Climate looks at what is the weather pattern. Now, when you talk about weather, that includes temperature. What else? Temperature, yeah, wind, yeah, the wind direction, and so on. Oh yeah, one more thing, the humidity. Yes, the humidity in climate. All of this information you always seen in Jabatan Meteorology website lah, where they exactly giving you this information, and you can get it from there even. But an extra information lah. Now all this climatology information from Jabatan Meteorology is not free. Yeah, you have to pay. Once you pay, then they give you the report. Yeah, only with that, then only you can do all this preliminary information. Okay, so it depends on the objective. Some you may use it, some you may not. But it's quite safe to say lah, if in air pollution or air, if you want to develop a plan to monitor air quality, most likely everything here applies lah. I can say all of them applies. Yeah, none of them will be excusable. Okay, so I think I've explained also the second point, so I think I can skip lah. Yeah. Okay, selection of sampling procedure. Now this one, there are several types of procedure that you can use. So you can see here, it could be continuous and time average in situ sampling. So when you look at the time here, you can monitor all the times that you want, or you can select only a certain time frame that you want to monitor. Now, why this is so? That is because sometimes the pollution doesn't happen in daytime. You see, if logically, logically, the polluters, okay, the potential polluters doesn't want to be caught by the authorities releasing toxic gases from the factory. Obviously, kan, logic. So logically also, most of the pollution, if there are polluters irresponsibly, they want to pollute the air at the expense of their cost, they will likely going to do it when the authorities are not working. Do you understand what I mean? That means late at night, at the dark, nobody can see the gas, kan? So everybody sleeping, then no problem, kan? Yeah, I'm just speaking from the ugly truth lah. In anywhere actually, if there is any pollution happens, they will go to release at night because that is the safest time. Authorities not there to check them. Okay, so that is why time average you can do it lah. Late night you do it. I mean, from 7 p.m. until 7 a.m. you can set the sampler to collect air samples during the time frame. And another reason why you want to put time average is that for cost reason, you cannot afford to collect samples continuously. Then time average, you can justify it. It's okay. Yeah. And when you look at here, the word in situ, of course, there is another version of it, ex situ. In situ versus ex situ. Do you need me to explain this one? In situ versus ex situ. Do you understand what is that?
In situ outside.
Yeah, in situ means you are collecting at site, right there, in situ. Ex situ means you are collecting it elsewhere. But most of the time, you can say lah, yeah, the in situ sampling is applied, because of course lah, air travels very fast. You cannot just like, I mean collect it in somewhere else. You have to be there. Yeah. Okay, so this continuous sampling is carried out by automatic sensors, optical or electrochemical, and spectroscopic methods, which produce continuous record of concentration values. The specific time average concentration data can be obtained from continuous records. Okay, what this sentence means is that the continuous sampling is measured directly using automatic sensor, and that is exactly what DOE, Department of Environment, and also Jabatan Meteorology, the meteorology department are using. They all use sensor, so practically they don't do sampling lah. The only sampling that may apply is exactly just outside of their automated sampler. That's all. So doesn't involve human at all, yeah, in this time in this sampling. So from here, time average data can also be obtained by sampling for a set of time, i.e. by sampling a known volume of air for required average time. Samples are then analyzed by established physical, chemical, biological methods for concentration values, which are effective average over period of sampling. So in the second data point right here, is just mentioned that you will collect it and then analyze it at later time. So from here, you can see there are two different methods. One in situ, immediately you get the result. The other one is you collect in situ, but you measure it using another method to quantify, okay, the amount of contaminants that you have. So the question that I want to throw you is that why there is two methods? Why can't you just use the first one? Continuous, straight away you know the question, the answer. Isn't that good? The first one, of course, is best because immediately you know how concentrate and how bad is the air quality. Now, this is important because when you know immediately that the air is not good, evacuation is needed. You need to evacuate the population so that they don't suffer the sickness. One good example, lah, yeah, one good example is in Pasir Gudang 2 3 years ago. Pasir Gudang during that time. Suddenly, during that morning, when school children go to school, they all fall sick. That is not really a good PR lah, for any government at all. But there's a long story there lah. Then maybe if we have time, we can discuss that. Because if they have a very good system to warn them when there's a pollution happen, they just close the school, ask the school children, just stay at home, don't come to school. That's it. And that is exactly the steps that the countermeasures lah that they can use. Yeah, stay at home, no need to come to school, otherwise they fall sick. Yeah? But the second one, why it is still applicable, although we cannot know the concentration of the pollutants immediately, this second method exists simply because not all pollutants can be analyzed by the first method, because some of the pollutants, they might not be even exist during that time. Yeah, it's just like COVID. Last time they don't have COVID, but suddenly there's a new virus called COVID. Yeah, pollutants, air pollutants also the same, because the complex reaction between human activities and new chemicals, they may create emerging pollutants, and new pollutants never seen before. So if that is the case, guys, then the second one is needed. You need to first, yeah, collect the air sample, extract all the contaminants or all the chemicals inside the air, and then you analyze one by one. There, and only then you have the ability to identify emerging pollutants. So these two still exist, even though the second one is not favorable, that they are there for a reason, because they are there to counter the emergence of new air pollutants. Yeah. Okay, sampling location, very straightforward. Identify the source, if you can, identify. Then you establish a transact or judgmental sampling. towards the area of interest, like the general population and whatnot. Yeah. But if you don't know the location, then simple, put a grid sampling, and then from the grid itself, you can identify lah, which grid has a higher concentration, and then there is your source. And then maybe you can have a second round of sampling to exactly lah, measure how is the distribution, yeah, of the pollutants. So there are a lot of points that you can see right here. Oh yeah, one more thing, the background concentration. So once you have identified the source, you will need to also identify the background. Now, background means uh, the level, yeah, the level of pollutants of interest without the source, yeah. That means some of the gases, like for example carbon monoxide or maybe nitrogen dioxide, they already exist in the atmosphere. Maybe those gases doesn't come from the source of the pollution, so that you have to remember. Now that also applies to many of the pollutants, like for example radioactivity. Don't don't be surprised, in natural state there are already radioactive substance around us. It's just high or low. So if you want to identify or pinpoint, okay, the pollution, yeah, the radioactivity coming from a source, you will need to subtract, tolak, yeah, subtract, okay, subtract, that means tolak the background levels first, because it's already there. It's not due to the polluters, but polluters add up. So you have to determine the background first, then only the source. Then it becomes accurate lah, the measurement, yeah. Otherwise kesian lah the polluters, everything salah dia kan. So background you also need to determine, and usually this background is the location which is far away from the source, yeah, from the source of pollution. Once you determine the grid, then you know lah where is the source, where is the background, yeah. And the number of location that you want to do this sampling based on how uh, how well the data that you wanted, and also how deep is your pocket. Of course lah, we want to analyze as many as possible if we have the money, but most of the time you don't, kan? So you have to be smart lah, determine the location where it will give you the best result, yeah. Okay, the period of sampling also we're going to add up into the number of samples, because the more frequent you collect samples, the more data you have. True. However, cost also the same. And it's not it's quite safe to say the cost of sampling is 10 times, around 10 times of the cost of the number of sample, and 100 times the cost of the cost of analysis compared to the number of sample. So it does add up lah, yeah, the cost. So it is preferable to observe sampling period consistent with the averaging times for which air quality guideline of the given pollutants are specified. So the second point mentioned that the average time. So if you still remember, each of the pollutants that we seen just now in the diagram on the national guideline for air pollution, the levels permissible, they were measured against a certain time frame, like 1 hour or 8 hour. So just collect according to what is required by the law. If the guidelines specifically use 8 hour time frame, then you collect all the air samples within that 8 hour. Yeah. So from there, you just need one air sample, but it is collected over 8 hours. Yeah, most of the guidelines used in Malaysia, the permissible levels of any pollutants, usually they are measured in an 8 hour time frame. Some may be shorter. If they're shorter, maybe the concentration is very high, so you don't have to collect 8 hours. Just 1 hour is enough. You can detect already. Now 8 hours is the normal lah, yeah. And vice versa, if the concentration of the pollutants in the air is very very low, then you may need a longer time frame, yeah, to collect it. So it all depends, yeah, it all depends on how concentrated is your pollutant, and also the authorities lah, yeah, the regulation, what the regulation wants, you have to follow. Okay, parameters. What do you need to measure? Of course, air quality index, air pollution index. So air pollution index in Malaysia, if you still remember, SO2, NOx, ozone, maybe not this one, carbon monoxide, PM10, PM2.5. But I've heard that in Malaysia, we already have a new one, a new air pollution index. You want to say new is not really that new because it is gazetted. It is gazetted in 2016. Quite new lah, not very old, not also not very new. So here is your assignment, your task. After this, go check the internet and find yourself this new, so-called new air pollution index. Okay, go check it out, and then once you have the answer, post in the forum. I'm going to open a new topic, a new forum, so you can post lah. What do you got? Yeah, the new air pollution index in Malaysia. So we were just going to follow that. This one, they are all from United States, so we don't follow lah. Yeah. Okay. So in addition, matters for meteorological parameters such as wind speed, direction, temperature, solar radiation, relative humidity are also discussed along with windrows plotting method. So I think these are very straightforward, but perhaps you haven't seen this word before. Windrows plotting. So this is actually a diagram where it shows the direction of the wind and also how strong is the wind. So very much this is a plot that you can see from the meteorological report lah. Uh, but in Malaysia, I haven't seen. I've seen this report before from Jabatan Meteorology. They have all these parameter, but they didn't show the rose plotting lah. That is the only difference. But it doesn't matter because you already have wind speed and direction kan. So wind rose giving the same information, so no issue. Okay, the rationale for selecting these pollutants in this manner is that they are ubiquitous in urban air, widely recognized as posing a potential risk to population health, and they are commonly regulated at national and international level. So, why this meteorological parameter is so important? For very simple reason. Pollutants in the air travels much faster than you can ever imagine. In a split second, with a strong wind, all your pollutants can be removed just like that. So how do you know that you have a pollution in the first place? So by realizing the movement of air from the meteorological parameters, we can actually estimate the mobility or the movement of these pollutants from the source so that we can track their movement and analyze them. Of course, when you have this kind of information, you also can better position your sensors in order to chase and track this movement. Okay, so no air monitoring is complete without this. So always remember, in any air monitoring plan or sampling plan, meteorological parameters is compulsory. You cannot do without it. Yeah, it must be there. Okay, students, we're going to restart 1 minute earlier because I just realized that I have like over 50 slides to go. So yeah, I better start earlier lah. Yeah. So I'm going to continue talking about the techniques. Yeah, the techniques on how to collect and measure pollutant gas. Yeah, in the ambient air. So this is a reference method for analysis of sulfur dioxide in ambient air, and the applicability is that it needs to be collected in 24 hours. Well, not exactly 24 hours, between 30 minutes to 24 hours, depending on the requirement. And then usually there's a advanced and not so advanced technique in order to determine sulfur dioxide in air. Like I mentioned earlier, there are like advanced equipments that can measure in situ immediately, tells you how much of sulfur dioxide, or you can actually trap this gas and analyze it later. So that is the second point. So what you can see right here is the technique to capture sulfur dioxide, and then it is measured elsewhere. So the chemicals that are used to capture sulfur dioxide is potassium tetrachloromercury. How this looks like, I don't know, but it does trap this gas, and then it will be transferred and reacted with another reagent, and this is acid bleach pararosanilin dye, and then it will going to give you a color. So from based on these two reaction, okay, the first chemical to trap it, the second chemical is to give them a color, and the intensity of this color is proportional to the amount of gas trapped in potassium tetrachloromercury. So the more intense means the more carbon, the more sulfur dioxide it is there. And these will be measured optically using spectrophotometer. Now, spectrophotometer is an equipment where you have a source of light and a detector. Whatever that you want to whatever you want to detect, the sample will come in between these two, and then they will go to measure either the absorbance, how much of light is absorbed by the sample, and how much of light that is transmitted. Now, in this case, spectrophotometer, they're going to use normal, ordinary light, but they're going to read the absorbance, yeah, at 548 nanometer. And then, of course, they're going to have some reference material to establish the calibration curve. And from there, they can measure how much of sulfur dioxide in the captured chemical, TCM. And yeah, just like that, they can measure it based on the comparison with standard. So of course, there are certain things that we need to be mindful. Once we measure this word, a lot of condition may apply because the conditions around us also will dictate how much of pollutants they will be there. So remember, yeah, it has to be corrected to the reference condition at 25 degrees Celsius and the atmospheric pressure. Now this one is the universal one that people use. Okay. And also, let's not forget when we collected this gas in this TCM chemical, it's very important for us to also determine the flow rate because air is bubbled through. You can bubble fast, you can bubble slow. The faster you bubble, the more air that will be transferred through TCM. That means if you use higher flow rate, that means more sulfur dioxide. But if you use a slower bubble rate, that means less sulfur dioxide. Now, this also you need because that will going to determine how much of air in terms of volume that you have collected. So it will be divided based on the volume of air that you have collected. But and that makes a lot of difference, yeah. So these are the method, instrument, and also auxiliary equipments that you need. Like I said, the last one, the auxiliary, the standard gas bubbles, last bubbles, and also the rotometer. Now, rotometer is the one that measures your flow rate. Very important that you need to know your flow rate, and it has to be constant during the sampling. Yeah. Of course, the instrument that we use to collect this one, to store your TCM and do all this sample collection, is an impinger. Okay, an impinger later I will show you. Or high volume sampler with a gasket attached to. So you can say impingers are old lah, the old technology. The high volume sampler may not be required all of them, but they may be attached lah with an accessory gasket, yeah, to capture sulfur dioxide. Okay, So you can see right here, this is the redundant information because just now I just mentioned TCM kan, but this one they use a slightly different chemical, sodium tetrachloromercury. It's the same chemicals to trap and absorb sulfur dioxide. So I don't need to explain this one. And the way they measure is exactly the same like earlier. You just add the chemicals, reagent, the dye to give sulfur dioxide its color and measure exactly at the same wavelength using spectrophotometer. Same technique, yeah. So this is the impinger or the sample tray. Impinger is right here. It's a glassware where you have like a stopcock. Inside the stopcock, you have a gas valve that connect into through a chemical that you're going to fill in this impinger. Now this chemical will be TCM, the chemicals that is used to trap sulfur dioxide, and it is connected directly into a pump. Now the modern impinger setup do not have this trap. Now, why you have this trap is just in case that if you're wrongly connecting this impinger, then if there's any liquid transfer into this area, it will not directly damage the pump because air pump is an electronic things, right? So chemicals cannot come here. So this one nowadays we don't have it lah because of the unlikeliness of having this mistake, and is connected to a manometer to measure the pressure of the air, and a flow meter to determine how much of a flow rate that is happening there. So the flow rate, there's no fixed number. It depends on you. You can control the flow rate as much as according to the requirement. And once again, what factor that influence the flow rate? How fast you bubble, and also how much of sulfur dioxide there's in the air. If there's very low sulfur dioxide, maybe you can use a higher flow meter or maybe a longer sampling time. Up to you. Yeah. So the next one is total suspended particulate matter. Now this one, we just going to collect air samples and determine how much of particles. Particles here is a solid, so very straightforward. You just pump the air into a certain area and trap all the dust that you can. So this one, I mean, no need to read all these points lah. It's not that important. And again, as you can see right here, it is collected in 24-hour window. Yeah, just 24 hour, not more than that. So from there, a sampler flow rate will have to be determined, and then it has to be sheltered lah, so that it doesn't uh, contaminated with some other things because anything can be floating from the air kan, yeah. And then the particles up to 25 to 50 micrometers will be collected, and of course lah, other parameters from meteorology department will need to be considered so that we know lah what is the dynamics of this, what causes they have higher TSP or whatnot. And then the filter use are specified to have a minimum collection efficiency of 99% for zero point 0.3 micron particles. So filters, they also vary. Some of them just to collect TSP, and some even better to collect PM 2.5 or PM 10. So these filters, they vary lah, yeah, and you have to use the correct one. Okay. Now, once you have collected the air sample, of course the dust particles were going to settle on top of this filter. But you have to remember, in Malaysia also is very humid. Dust, being very small, will logically absorb some moisture. So you have to determine also what is the moisture, and then you have to subtract the moisture, and of course other other conditions will need to be corrected according to what I mentioned earlier. Then only you measure, okay, then only you wait, okay, you wait the TSP, you wait the dust trapped on the filter to determine the TSP. Just like that, it's just like buka motor, trap all the dust, and then you just wait, of course lah, correct it based on the moisture. And then you were going to, well, because the weight is determined, so of course that obviously it will comes under SI unit gram, so you will convert it into microgram over standard volume of gas that you've collected in cubic meter. Very straightforward, nothing too difficult. except that you haven't seen the machine. By the way, I just want to ask question before I continue. How many of you have experienced or have seen a high volume sampler, air sampler before? Have you all seen one or experienced or used one before?
Not yet, sir.
Not yet, yeah? Okay. Um, I assume all of you haven't lah, yeah, because you haven't given me the answer. But don't worry, later on I'll have a video to show if we have enough time lah, yeah. So I'm going to, yeah, next one, sampling method, TSP, SPM, filter, auxiliary. Now this one is the redundant information lah compared to the earlier one. So I just skip, same here, skip. And this is how it looks like. So if you want to look at the schematic diagram, this is how it looks like. But the actual high volume sampler may not be like this. But oh wait, now I know why. Because this is a SPM sampling tray. So it does have an inlet to draw air and is connected to a pump. And in here you have a sample bottle where you have a cyclone. So cyclone is where it is concentrating all the dust particles, and on top of here it might comes up for the lighter particles, it might comes up and then it will be filtered by a gas cover or a gasket. So from this filter is where you can collect lah, either TSP for determination of TSP, or maybe determination of PM 2.5 or PM 10. So this is where it connects lah to a pump, a suction device. So this is SPM sampling tray, high volume sampler. At the last slide, I believe, of this lecture slide, I will show you. Yeah. So moving on, carbon monoxide and even carbon dioxide also. So when we talk about carbon monoxide, that also applies to carbon dioxide. Now these two gases, they are toxic. They are also a greenhouse gas. Uh, why do we determine? Very obvious, carbon monoxide kills. And for your information, now in Shopee, you also can buy yourself a detector, carbon monoxide detector, if you want to, and install in your home. Yeah, especially if you smoke. If you smoke, then maybe this is good for you because you never know. Like that. Okay. Now, how this what they call determination works. So they're going to use advanced technology using infrared infrared spectrophotometer. Now that is because when any chemicals, including gas, are being irradiated with infrared, they will vibrate. So once they vibrate, they will going to release an emission, or using this phenomena, they will absorb. So the absorption of infrared, you can detect its absorption. The emission, you can also detect its fluorescence. But the recent technology of gas sensor, the in situ gas sensor, they use absorption. They use absorbance, yeah. And this is quite good because so many data can be logged on a very small time frame, and you can know the result immediately and fairly accurate. It's fairly accurate, yeah. So what happened here is that the air is drawn into this sample chamber where there is a UV light irradiated through this chamber, and the absorbance will be measured. So they go to measure against the background, and there you go. You straight away know how much of carbon monoxide. Now that is because the absorbance, yeah, is proportional to the amount of carbon monoxides. So the more carbon monoxide, the stronger the absorbance, and the computer will pick it up and they let you know. So as simple as it is. Well, sounded simple, but it is not actually that simple. I if I can share lah, I have an experience looking at Pasir Gudang data coming from this infrared machine. They are so big that it took 1 hour to download that data, because it is measured in minutes, not in hours. So you can, I mean, earlier we discussed about hourly sampling frequency and interval, but this one in minutes, and they measured not just one, not just two, but 2,000, 2,000 contaminants in the air. Believe it or not, that instrument is that advanced. At one time, it measures 2,000 chemical at one go. That is why it took me 1 hour to download that data. So infrared. So I just want to stop here for a while. When we're talking about this infrared detector technology, essentially you don't need to do all this other sampling. You just use that machine. The machine will tell you immediately what contaminants, how much, what time, where, straight away. And for those who don't know lah, they are all in Pasir Gudang right now. Now because 3 years ago there's a fiasco that happens in Pasir Gudang. The government pumped in so much money setting up an advanced alarm alerting system in Pasir Gudang. They're still testing it, and they're very advanced. I can tell you, very very advanced. Up to 2,000 chemicals they can measure at one time. So advanced. Yeah. So that means we no longer need to do sampling. Actually, yeah, quite safe to say we don't need to do sampling with that machine. Yeah. Okay, next one. Okay, this is the same thing. Using NDIR method, which is like I said, infrared. This one also will be measuring carbon dioxide and water vapor, but it can be excluded because why? Now each of these chemical they have a unique signature pattern in infrared spectrum. So the computer is pre-programmed to exclude lah. If they can pick up the pattern coming from carbon dioxide or water, they just subtract it and there you go. Self-correcting this data. Yeah. Okay, so the next one. Now let's say if you don't have the instrument, you have to use the ancient, not to say ancient, the old technology, older technology. You can always use other chemicals lah. Um I believe there's one, but I think this slide doesn't tell you that. Now, what I can see here, the chemicals right here. Now, this one is still, this page, this slide, still talking about NDIR technology in detecting carbon monoxide. But this chemical here is still being used because magnesium perchlorate is used to absorb moisture from the air. So before the air reaches the NDIR gas chamber for detection, it will be first dried using magnesium perchlorate. That only comes in. Yeah. So that is the only chemical that is used using NDIR technique. Well, this one is not NDIR, but it's more of a personnel active sampler that is worn by a worker trying to detect a gas or contaminants indoor. So this one is not NDIR lah. NDIR is much bigger than that. Okay, next one is to measure the ozone. Now ozone, in order to measure that, we use a principle very similar to NDIR, but this one we detect its transmittance. Now the principle is based on the nature of ozone can react and absorb. Okay. Now, in this case, ozone reacts readily with ethylene or acetylene to emit light because they combust straight away. But I believe the next slide is not according to this one. What I can say is ozone reacts with ethylene readily to emit light. But the way we measure ozone is somewhat a bit different, in which um, we're going to still use photometer. We're going to use photometer, and it is very similar to NDIR. So I won't go to elaborate on this one because it's similar to the previous slide. Yeah, this one. Yeah, this slide exactly explain how ozone is measured. Yeah, using photometer. Now, in this case, the ozone will be detected at another wavelength. It's at 254 nanometer. So at this wavelength, it is already in the ultraviolet range. So this is ultraviolet. Yeah. Now that is because ozone have double bonds that can actually absorb this light, and they have a signature. They have a signature absorption at this wavelength, and the very much similar things were going to happen just like NDIR. Air samples flows into the gas chamber, and then they're going to have a ultraviolet light source, ultraviolet light source that is emitted, and they allow the ozone to absorb. So the more they absorb, the less ultraviolet we're going to pass through and picked up by the detector. Now, in this technique, it is slightly different. Okay, it is slightly different than NDIR, in which it differs in this way. Because earlier, when we discuss about carbon monoxide, we detect its absorbance, but for ozone, we detect its transmittance. It is interrelated simply because when you have more absorbance, you have less transmittance. Okay, and if this okay, now this is the formula for transmittance where I over I naught. I is the intensity of the light source. If this one is converted into absorbance, then the one on top will be I naught, whereas below is just I. So that is a relation lah. It is inversely proportional, I would say, the opposite. Okay, transmittance is the opposite of absorbance, and it is represented by this formula in which alpha is the absorption coefficient. You see, absorption. See, because they only have absorption coefficient, they don't have transmittance coefficient. They only have absorption coefficient. Each of these contaminant gas or any gas molecules, they will have this. Okay, and then C, right here, C is the concentration of ozone, and L at the last part, L is the path length. That means the length of your gas chamber. And all of this, if you still remember physics, lah, yeah, physics or chemistry, physical chemistry in secondary school, you have learned Beer-Lambert's absorption law. This is what they have mentioned. But of course, lah, this is not chemistry class, guy, but I just want to let you know lah, how we calculate transmittance, okay, by using this. Okay, so yeah, this one redundant. And as I said just now, a UV calibration system, because at 254 nanometer, that falls under UV range, the electromagnetic wave. Yeah, the light source that is used to detect ozone is of a UV lamp, like you can say. So what about zero air? Now, zero air is the air that is free from contaminants. That means no ozone that has to be drawn in. So you can say zero air here is to measure the matrix and also serve as a background also. Yeah? The the background of the detection of ozone. And then the next diagram will shows you how it works. So zero air coming from here, and then this will be mixed with the ozone generator where it will going to provide them with ozone. But if this one is in ambient air, you can say that this one is ambient air, and the air, the zero air will be sourced from somewhere else now without the presence of ozone. So they're going to come in, draws into this UV photometric calibration system, and they're going to start with the absorption. Very much similar to what I've mentioned earlier. Yeah. So remember, yeah, ozone, we measure the transmittance, whereas the others, they are very much on the absorbance. Yeah. So nitrogen oxides also very much the same. It can be measured using NDIR as well. Uh, but we do have another way, alternative way of doing things. Yeah, like you said, the NDIR technique is measured at 600 nanometer. So that is a wavelength of uh, for specifically, okay, this is a signature wavelength that people use to detect the absorptions of nitrogen dioxide. Now in this case, it can be converted first into nitric oxide, and it's measured in, let me see, I'm just not sure whether, because when I read this one, I thought that 600 nanometers is for nitrogen dioxide indirectly. Oh yeah, sorry. If we say indirectly, that means 600 nanometer, that is a wavelength for nitric oxide. That is for nitric oxide. So for the detection of nitrogen dioxide, 600 nanometer is the signature wavelength for nitric oxide, yeah? Nitric oxide, not nitrogen dioxide. So in order to be converted here, they just react with ozone. Yeah, reaction of nitric oxide with ozone. Then they measure at 600 nanometer. Okay, now what about the others, nitrogen dioxide? Well, there's a way to detect both nitric oxide and nitrogen dioxide, in which first you can convert all the gases, nitrogen dioxide into nitric oxide, and measure it. Okay, so that one as the first reading. Now the second reading is you do not you do not convert. Okay, we don't convert nitrogen dioxide. We just measure as it is. So the balance. Okay, the difference between the first reading and the second reading gives you an indication of how much nitrogen dioxide is. So that is the whole point. That is the whole idea on how to detect nitrogen dioxide versus nitric oxide. So, well, there is another method, an alternative method by trapping using chemicals and measure it later. So this method, we use a chemical, a combination of sodium hydroxide and sodium arsenide to absorb nitrogen oxides. So once this is absorbed, they will be um, they will then be mixed with another reagent. Now this reagent will give itself a color. So it will going to mix with phosphorus acid, sulfanilamide, and also NADA. Now NADA means N-I-naphthyl ethyl dichloride. Yeah, it's a long name, so that's why they call it NADA. So all the combination of these three chemicals gives color to the nitrogen oxides trapped in earlier sodium arsenide. And of course, just use photometer. Photometer, light, you just shine it and pick the absorbance at 540 nanometers, and there you go. You know how much of nitrogen oxides. But this one did not say how it separates between nitric oxide and nitrogen dioxide. So maybe that is a downside here. They don't tell you how much of nitric and nitrogen dioxide compared to the one earlier, NDIR. So again, the setup looks familiar, kan? It looks familiar with sulfur dioxide is because that is a technology used by any gas. If you want to trap it, exactly the same setup will be used lah. And that is also why impinger usually they don't come as one unit impinger. They come with a series of it, depending on how many gas you want to trap. So if you have a time later and you search Google or you search YouTube, you can see there's a train. Train means a series of these things. So this one trap one gas. You can have another replicate of this one, trapping another type of gas. So it is arranged so closely together that it looks like a train, but it's not really a train, but it looks like one. So that's why they call it sampling train. Okay, so this one is suspended particulate matter. Or lead, sorry, lead, yeah. Now lead, to determine lead in ambient air, usually lead is not a gas. Lead definitely is not a gas. It is a solid, no matter what. So that is why, in order to detect lead in ambient air, we just determine how much of lead based on the suspended particulate matter. Okay, collected from ambient air. So if you remember just now, total suspended solid, okay, total suspended solid, you collect it. Yeah, right here. Total suspended solid you collected in 24 hours, high volume air sampler. So the dust, the same dust that you determine total suspended solid, collect it, and then you digest. You digest using nitric acid. So all those dust were going to dissolve under nitric acid, and then after that you determine using ICP ke, to determine how much of lead inside this nitric acid. Simple as that. Yeah. Or you can use another technology, the older one, I'll call it atomic absorption spectroscopy. This one use acetylene flame, blah blah blah, very manual. You can say lah nowadays lah. Nowadays, not many people are using it unless you are very cost effective lah. I would say because why? AAS is very cheap. ICP quite expensive, but if I can choose, I would choose ICP because ICP can detect so many elements at the same time, just like NDIR. Okay, so next one, straightforward. PM10, how do we determine? It is exactly like total suspended solid. Okay, the only difference between total suspended solid is on the filter. Of course, lah, you want to detect PM10, guys, so the filter have to be small enough, the right size to trap PM10. Now, maybe there is a stack filter inside high volume sampler in which not only you can detect and trap PM10, you also can track can trap PM 2.5 because these two just based on different particle size. They all from the same thing, dust, TSP. So you can say TSP is the sum of PM 2.5, PM10, and PM and particulate matter greater than PM10. Simple as that. Just the filter lah that differentiate them. Yeah. And because of that I will skip because this one how they were collected is based on the filter and also some mechanics on how they were like collected. So this one I'm not so sure myself how inertially separated they are, um, because inside the video also they never show. I have to concede lah. I haven't handled one myself, but hopefully in our field trip, our academic visit to Sugarcane, hopefully they have one. If they have one, then we can have a better picture on how this PM10 is collected. Of course, correction against the natural condition, 25 degrees Celsius atmospheric pressure, and again, the unit being used very similar, exactly the same as TSP, microgram per standard cubic meter, same unit. So this is the 2.5, also the same. Again, 24-hour time frame, exactly the same with PM10 and TSP. And again, they use a very special filter to trap PM 2.5. And that filter is made of polytetrafluoroethylene, PTFE. Ever heard of this material, PTFE? Maybe you didn't pay attention when you buy a air purifier. How many of you have air purifier at home? How many of you?
Doesn't have some
No, I don't have.
Yeah, I understand. Very expensive, guy. 500 per unit. Who wants to buy that one? But it depends. Like, let's say if you have a relative or a person at your home that have asthma, I think this is a good investment because every asthmatic attack rises from particle, especially irritant. You never know, right? Uh, some air purifier are very cheap, like 1 200, but I recommend you to buy a good one. Yeah, 1 200. I think you better don't buy lah. Yeah, it doesn't filter as much and it doesn't last long. The advanced air purifier. Why I bring this up is because actually air purifier is just like mini high volume air sampler. They have pump, they have filter. They sometimes also may purify some dangerous gas. And the latest one, the latest one actually tells you how much of toxic gas as well. I don't want to say the brand name lah, but I think you can discover yourself. Some brand can be that advanced to tell you how much of PM 2.5, how much of PM10, just using just from the air purifier. So if you have money lah, I'm not sure if you still eligible to receive duit raya kan, but I mean if you have enough duit raya lah, 500 is a good investment if you have asthma. If you have asthma, buy one, very good one. And their filter, why I bring this up, because their filter inside there, PTFE, exactly this. And one more thing, PTFE is not cheap. It is damn expensive. If you want to replace one filter, it's 1 to 200. It's like 30 to 50% of the price of the air purifier itself. So up to you lah. If you have asthma and this is good for you, it is definitely a good investment lah. I mean, your health versus 500. Come on, 500. I mean, that is like nothing compared to your health. That okay, particulate matter 2.5. Now, why this is important? Because nowadays, a lot of 2.5 coming from dust, especially smokers. If you have people smoking inside your house, PM 2.5 is guaranteed other. You just wait for it. Yeah. But another issues that arise nowadays is that just several days ago, people say that microplastic is detected in human lung. So out of this PM 2.5, then there is an increasing proportion of plastic here. So I'm not trying to scare you to buy air purifier, but that is the truth lah. So maybe you can consider like allocating this year 500 ringgit buy air purifier. If you have health lah, I mean especially your lung health is not good, buy one. It will improve. Yeah. Okay. Reference method. This one I'll just skip lah because I think very similar. Yeah. PM10, PM 2.5, TSV, they're all using the same time frame of sampling. It's just the filter that is different. So yeah, I'll just skip. Same thing. Applicability and definition. Well, very similar also. So I just skip. Yeah, redundant information. I'll skip. I have mentioned I will talk about this, so I will skip again. Yeah. Finally, how much time do I have? 10:30. Oh yeah, now good. I have half an hour to show you this video. So these are the images or the schematic diagram of high volume sampler right here, and also the PM10 samplers. Well, essentially they are almost the same. The assembly also tells you they're almost the same, except that their filter is slightly different and they have flow control. Both of them will have flow control. The setup is more or less the same. Now, I I think you should watch yourself lah. Now the video on operating A and B, high volume sampler, they are in this last two video. High volume sampler video 1 and video 2. This video was taken by a student in University Malaysia Terengganu, and they have one brand new high volume sampler there. So the lecturer explained and showed them how it is used. So you can watch these two video lah on these two. Why I asked you to watch it, because each of this video takes up to 10 minutes. So yeah, such a such a waste of time. You can watch it later lah. Yeah. High volume PS1 sampler also looks very much the same as high volume sampler others. PM10 sampler the same. So you can say A, B, C, F, and G. They are the same thing. They are the same thing. Yeah. Now what is not the same is this one, personal sampling pump. Now, if you still remember just now, this pump. Wait, this pump. This one is the personnel sampling pump. It is worn at the waist level, and then this one connected through a tube onto a device, and it is attached to a person's neck. Uh, so let's come back to this diagram, and I hope you can watch this video. Um, Okay, what do you think? Do you want to watch this yourself, or do you want me to finish early and watch this video yourself, or you want me to tayang here, to air it here? Which one do you prefer? You want to watch yourself or not? What do you think?
If we have enough time right now, we
Okay.
can watch now.
Yeah. Initially the intention is to show it to you and let you all watch right now. um, but I haven't tried because there is a possibility if I share here, it is without audio. So let's see lah. Yeah, let's try. I will stop sharing first. I will stop sharing first and then see if I can share this video with audio. Wait, okay, hold on. Let me share. I hope it comes with audio lah. So, tap. I'm sure you can see what the YouTube, right? Air sampling question and answer. Can you see it?
Yes.
Can see.
Okay, I'm going to play. If there is no audio, let me know. Yeah, got audio or not?
Mm, no audio.
No. No
Yeah,
audio.
you see that is the problem lah. When I use Webex, they have a different function and you have the audio. But if I play here and I share it, that's a problem like that. It doesn't have audio. And I don't think Microsoft Teams have the ability to share audio. So okay lah, what to do? Okay, I'll stop sharing. I will finish my lecture and let you yourself watch the video lah. Unfortunately, it have to be this way lah. So okay, let me finish lah. Okay, wait. I haven't shared the PowerPoint slide. Wait. So coming back to here, that is a personal sampling pump being used to measure most likely indoor air because personnel works in indoor environment and most this is very popular lah, as one type of active sampling. Active sampling means it will involve energy, it will have pump, so it keeps on pumping air into its sampling filter or chamber. Now, canister sampler is another type of is another type of sampling technique. We call it passive sampling. So passive sampling does not require energy input. You have a sampler, you take it out, and then let the air naturally goes into your canister. So no energy involved. And the big difference here is that passive sampler usually very cheap. And this is very popular, like, especially for any research that doesn't have too much of what they call budget to operate. And so it depends lah, depends on the interest lah. Yeah, they both have pros and cons, and you can look for it by yourself later. Yeah. So other things that is involved in the air sampling is the rigid whole air collection canister or SUMA canister. Right here, air. The A diagram is like a metal stainless steel. I will call it stainless steel device where it is initially pump out of the air. So inside initially, this SUMA canister is vacuum inside. Okay, it is vacuum. So you're going to bring to the side, turn the valve, and allow air to slowly goes in. And as you can see here, you have a barometer that shows you the pressure inside this SUMA canister. So eventually the pressure will going to rise until it is equivalent to the atmospheric pressure. So once it is equivalent to atmospheric pressure, then you know lah, it's no longer drawing air sample into its canister. So by that time, it will be closed off and sent for further analysis. Now this device has been used many times before, but given with the advanced technology of NDIR, sampling is no longer something that requires SUMA canister anymore because of the steps, the tediousness of this, and then the limitation in sampling air because it only limited to this small canister. How much of air can you draw? Not much actually. Yeah. Uh, So B filter cassette for particulate sampling. Now this one is another example of passive sampling. Is a cassette. Sometimes it is uh, right here, yeah. So this is a cassette. It is a device that you can, if you pull it out, you have a series of layers of components being assembled together. And inside this filter cassette, you will have maybe some membrane for you to filter the particulate. Some of them may be attached to a pump, some of them may not. And for those who doesn't, it doesn't that is not attached to a pump, it can be as simple as a petri dish. A petri dish where you put grow media, a medium broth. And when you want to sample the air, like usually the petri dish passive sampling is to sample what kind of indoor air microbes. Okay? Indoor air microbes. So it had to be initially sterile. And once you go into a setup, an indoor setup, and you want to sample the air, you just open the lid, expose the petri dish into the air for a certain time, close it back, and just wait. Wait for its culture to come up. So once the culture come up, you isolate it, then you know what kind of bacteria is that. Impinger is something that we have learned just now, so I won't go to touch about it. Sorbent tube cartridge. So this one is right here. It is one type of a passive sample, but I have no idea how it is used, but you can always watch this video. And lastly, polyurethane foam, PUF. This one also is a form of a passive sample. And yeah, once again, it does have video. Now, because of the limitation of Microsoft Teams, I cannot show you the video, but the PowerPoint slide is right here. Uh, Now, for those who have already checked the PowerPoint slides from UFuture, you will notice that these last two slides actually is in 5.0, lecture slide 5.0. So I skipped the entire slide of 5.0, only extracting the last two slides and then bring it here. So that's it. What you need to know about ambient air sampling, and some of this so-called ambient air sampling also is subjected to indoor air sampling as well. So that's it. Everything you need to know about air sampling. Video, watch yourself. Any question, post in the forum in UFuture. So with that, I end my lecture.